This is a pedigree. Pedigrees are kind of like doing Punnett squares backwards. So you start with the offspring to help you figure out what the parents are. Alright, so we've got square and circle. Squares are always male, and circles are female, because females are curvy, right? And because males are blockheads. Haha. Then we've got, that's a marriage line going across, and that's the child line coming down. So we've got this square, so that's a male, and since he's all the way on the left, that's the firstborn child. Then we've got a circle, and we've got another circle that's not filled in, and a square that's not filled in. These are the children of these two parents. These children are grown, though, and they've been married. So here we have the wife of that one, and then here we have the husband of this one. That one's not married. This one, we have a wife. Alright, and then the reason that these two are shaded in is because they exhibit the trait that we're looking at today. And this trait is albinism. Or albinism, that means that you don't have pigment. Okay? It does not tell you in the question whether this is dominant or recessive. That's something that we're supposed to figure out. And even without doing the next generation, you can go ahead and figure out dominant or recessive, because if you have an individual with a disease and the parents don't have that disease, then you automatically know it has to be a recessive disease. Because if it were dominant, then, and it came from one of these parents, and one of those parents would have to also be shaded. And they're not, so therefore we know it's recessive. However, we do know if this is recessive, so we'll go ahead and write little a under these two, because we know they have to have that particular genotype. Where did that little a come from? This is backwards Punnett squares. That little a had to come from one parent, and the other little a had to come from the other parent. Do we know what their other allele is? Yes, we do, because are they albino? No, they're not, because they're not shaded. So that means they have to also have the dominant allele. Okay? Cool? That's not so bad. Alright, so moving on. I don't know. I know this is a big A, but I don't know what is here, because it could be big A and big A, or it could be big A and little a. And there's no way to tell. So we'll just put that line there that means that we don't know what that is. Alright, so then we're going to look at the offspring. This particular person, we've got person 4, circle, square, and square, and none of them are shaded. Every single one of these offspring had to get a little a from that parent, because that's all he has to give in terms of that gene. So they're all non-shaded, so that means they all have to have what? A big A, which would have been from the other parent. So we've got big, little, big, little, big, little, and big, little there. So do we know what goes right here based on these children? These guys all got a big A from her. Could she have a little a there? It's possible that she could, and that they got really lucky when they had all these 4 kids that they all are normally pigmented, but it's not likely. So more than likely, this individual is big A, but realize that I'm putting a star there because that's a most likely, it's not a definite. Okay? Alright, then we've got this next set where we have shaded, son, unshaded, unshaded females. Automatically we know shaded is always little, little, and then these we know have to have at least one big A because they're not shaded. What's their other one? Has to be a little a because that's all that parent has to give. Easy? Okay, and then last over here we've got 4 kids. No, 5 kids. Busy mommy. Alright, so we don't know. We know that they're all normal. We know that this person has at least one big A. This person could be a carrier. They could be Big A, big A. We don't know. Okay? So is it possible to tell for sure what that person's genotype is? Not based on this information. Because if this wife is big A, it doesn't matter what that is. There's no way possible that they would have an albino child. Because every one of them would get a big A from her. So then you have no idea what that second one is. Okay? If she's a carrier and he's a carrier, then chances are you'd have at least one that was albino, but not necessarily. Well, that wasn't the one, but this one over here. But anyway, you can't tell for sure. So on the question where it asks about him, we don't know for sure because of the fact that we don't know her situation. If we knew her situation, then we could have at least a better estimate for what he would be. Alright, so that's our pedigree problem. Number 10. Let me erase this. Don't you guys just love genetics problems? This is my favorite section.